Okay, so I will be again to my iPad and talking about the bipolar transistor before we're coming back with the handout. And also today at 6 o'clock, one guest will be talk to your guy about the job. Okay, I believe everyone really want to know. You can see it?
Yes.
Okay, good. Okay, so this is a new chapter in electronics. So if you're looking into that display, there's a symbol for the transistor. One will be NPN and another one will be PNP. Okay? And you get just about field formula. IE equal IC plus IB. If IB is too small, then IC can be equal IE. And you can get a alpha is the ratio between IC and IE. And a beta also equal IC over IB. Okay? So now, before we start it, we need to know that's what we call P-N junction. And we already know this basically just a diode. Anode, cathode, and that VD, VA, minus VC. And they will be equal 0.7 volt for silicon and 0.3 for germanium. That's what we already done. Okay? So you every time you see that a PN junction, that's just a diode. Okay? Now we're talking about a transistor.
When you're physically looking at a circuit board, can you tell the germanium from silicon, or do you have to look at the prints for that?
They tell you by the part number. But the thing is, most of the time, you will be saying that will be silicon. We deal with 0.7 all the time. Okay, so now talking about NPN transistor. So basically you see NP, that means you get the diode, right? And there's another diode. So basically that will be the base, okay, emitter. And that will be collector. So that will be, if you're looking into that, you can see NPN basically you get only two diodes, okay? And now the symbol will be, okay, that's a symbol. And that will be the base. That will be emitter. And that will be collector. Okay? Now, when you're looking into this NPN, where is the two diode? First one, you can get a one diode right here. Another one will be diode here. That's what you get two diode right here. Okay? And this diode here, they will be around 0.7 volt. So you want to turn this diode on, the voltage at the base must be higher than 0.7 volt. And the current get collector here, emitter here, and that is the base. The current must be go this way. IB coming in, IC coming in, IA will be leaving. If any question, let me know, okay? That's just a formula. We must be following. So when you see the symbol, that means the symbol right here, arrow coming out. That will be NPN. If they coming in later on, you see that PNP. And also again, you can see you get a two diode, okay? One from base to the emitter, another one from base to the collector, okay? So you get through that one. Any question? That including inside your handout. However, I want to make sure you understand. And quickly I go to the PNP, okay? You can say P and P. And you get P and get a diode here. And you get another one. Okay? Still the same thing. You get a collector, emitter, and that will be the base. And this is a symbol. Okay, the arrow coming in. Okay, collector, emitter, and that will be the base. Okay, and the current flow. IC coming in, IB coming out. Sorry, IC coming out. And IE coming in. Okay, that is the difference. But the formula will be the same for both types of the transistor. Okay, any question?
Yeah, I have a question.
Yeah, go ahead.
Okay, what is transistor? What is the purpose of using a transistor?
Can you,
What is transistor and what is the purpose of using a transistor? Why we use a transistor?
okay, we'll be telling you.
Mr. Pham, that's the bipolar transistor you're describing, right?
Bipolar.
Okay.
That will be tried to later on. If you're talking about transistor only, later on you can get another different type. They effect. Okay?
Okay.
Hey, Mr. Pham, before you erase that, a question. On the, because this is just a refresher for me, but on the NPN, the current comes in through the collector, the base goes like up towards the base and then over to the emitter. But on the base on the NPN, it goes emitter out of the base and then some goes out of the collector. Why is it like that?
Now don't ask me why. That's the formula. That is the way they will.
Okay,
Okay?
all right.
You want to know, you want to learn, you must be follow at least the basic.
Okay.
Okay? Now, the transistor will be working in the three modes. Okay? That means they get to do three things. Number one, called active. Active means you want to be amplified. That means they're using the transistor to build amplifier. Okay, second one, they can be saturation. That to build the logic. Okay, and number three, they will be cut off. That for switching. That is the three things the transistor will be doing.
Yes, thank you, I got it.
Yeah, you want to be build the transistor as an amplifier. That means when you're talking, that means your sound wave, they go to the microphone, they converting to electrical. If they go to the amplifier, they try to make sure your voice will be bigger. Okay, that's the amplifier. Now the next will be saturation. Saturation, that means they're using the transistor to build the logic circuitry. When you go tech school, you can learn inverter, AND gate, OR gate, NAND gate, counter, flip-flop everything inside just the transistor. However, they must be working in saturation, not amplified. Okay? And the cut off, that means they're using to build a switch. Switch means you can open or you can close. Okay? Now, I'm talking about the switch. This is a transistor here. Okay, that will be 5 volt. And that be in here. If V in equal 0, what the voltage here? If V in equal 0,
Is
what
the
the
switch
voltage,
open or closed, Mr. Pham?
what voltage at this point?
5?
Very good. Okay,
And Mr. Pham, is that a resistor in the collector?
right.
Okay.
If V in equal 0, you understand from the base to the ammeter, you get a diode here. You need 0.7 volt to turn on. And now if you get a 0, this diode will be off. So basically the transistor will be cut off. Cut off means the transistor will be look like open, open, open. No current flow. Okay? This is a transistor. Cut off. No current flow. Open circuit. Okay? Open circuitry means no current can be flow. Okay? So that's why if no current flow, you get a voltage drop across RC will be 0. No drop. So that's why 5 volt here, you get 5 volt here. Okay? So basically you can see this like a switch. Okay, so when they open, that means this switch will be open. And now, if you apply 5 volt here, so the transistor will be on. When they on, that means they allow current flowing from IC to IE. Okay, and look like the transistor now, they will be connect this side like a switch here. They let the current flow. So that's why they will be closed. Okay, so the current can be flow down here. That will be cut off. Okay, more picture, more for clear for your guys in the handout. But I want to emphasize here, transistor, they will be working either they will amplifier or they can be saturated and they can be cut off. Okay, you get to know for your knowledge, but you don't get the thing that you not design. Okay, so that doesn't matter. Now, we'll try see something else. Okay, let's see. Okay, now they're giving you a little more picture here. Okay, so basically they just display, okay, you get a PNP or NPN physical, okay, physical for the transistor, we don't care on the physical. Only thing you need to see in NPN here, how the current flowing and with the arrow, okay, and this arrow coming in. So that's why that PNP and the current will be IE coming in, IBIC will be leaving. Anything. Now, like I said, region for operation. First thing, cut off you in the switching application. That means the switch can be open or it can be closed. Open means the transistor not working. Okay, close means the transistor will be working. Okay, saturation is in switching application or to build logic circuit. Okay, and active using for amplification. You want to design amplify, they must be inactive. And last thing, breakdown. You will cook the transistor. Okay, so in here they explain to you cut off diode from B to S meter E off. Like I said, that diode B to E not working. So that, yeah, the transistor will be off. Yeah.
Could you close your sidebar so we can see your full page, please? Your side where it says all pages. Can you close that so we can see the entire page? Thank you.
Inside here, right?
Where it says active diodes down there on the bottom, we can't see what it says to the right.
Active diode. Oh, okay. How come? I don't know why. Even I already draw on the right side.
Mine's fine.
Okay. I'm sorry.
It just says diode.
Yeah. Basically, active diode from base to the emitter ER, and the diode from base to collector ER. Cut off diode from base to emitter off. That enough. Will be cut it off. Saturation. Then both diodes are on, and the voltage from the collector to the emitter will close to zero. That's basically definition. Okay, so you understand inside the transistor you get the two diodes. One diode goes from base to emitter. One diode going from base to the collector. Okay, if the diode from base to the emitter not working, transistor must be cut off. No current flow. Open inside the transistor. And if they active, then the diode from the base to emitter must be on, and the diode from base to the collector have to be reversed bias. That means off. If both diodes on, they in the saturation. That's how transistor can be cut off or active or saturation. Now, on this one. This one is the graph for the IC versus VCE. So if you're looking on, we're going up this way. This stands for IC, and this one VCE. Okay, now you can see they given to you three area. You can see the area here. That's for saturation. The area down here for cut off. Okay, and the region in here that will be for amplifier. Okay, now this value here stands for what? Who know? Here or here or here.
Is that like base current or something?
Stand for what? I said one going up this way. I see. One going to the right. That VCE. What does stand for X value here?
The base current.
Very good.
IB.
That will be IB. That means on this line here, IB equal 100 micro, 80 micro, 60 micro, 40, and so on. Okay? Now, if I get the point at this point right here, can you tell me what is the IC equal?
Nine milliampere.
IC.
Around 9 milliampere.
Yeah, very good. You want it, you have to go to the lab, right? You can get some value here. So for IC. And now what the value for VCE?
10.
You going
Down.
down. That's around 10.
And IB equals 60 microamps.
Yeah, IB equals 60 microamp. So when you get the IB, you're able to identify IC and also identify VCE. So basically, this is IB control the current and the voltage, right? You change IB, you change IC, you change VCE. You get that? So that's why bipolar transistor, okay, a bipolar, okay, transistor, a current controller. Device. Okay? So remember that they will be asking you. Bipolar transistor is a current controller. Why? The thing is you change IB and you change the current IC and you change the VCE. Basically, that's controlled by the current IB. That's why they call current divider, a current controller device. Later on, you can get another transistor. We call it JFET. JFET will be the voltage controller. Okay? But for now, make sure transistor bipolar will be current divider. Okay, any question? That normally designer, when they design using the transistor, they have to know what they want. They want it to be an amplifier, or they want it to be saturated, or the cutoff. Okay? Now, if they want design an amplifier, then they can pick up one point right here. That's what they call a Q point. Okay? At that point, you're able to know what IC, what VCE. So you can select the resistor in order to make that. Why they don't want to pick the point in here? Who knows?
It's too close to saturation.
Yeah, that's too close to saturation. Okay? When the temperature raises, this point can be moved to the saturated they don't want. The thing that they want amplified, they must be amplified anytime. Okay? Cannot be saturated. So that's why when they design the transistor to do things, and they have to know what they want, and they have to select a certain point on this graph. Okay?
Hey, Mr. Pham, what's a good values? Was it, like plus or minus 10% saturation, on that line you don't want to get too close to?
Yeah, you don't want to get too close to the saturation.
Yeah, but I mean, what is it, like plus or minus
No,
10%?
We're not going into too much detail on that.
Okay.
Designer, they have to know. However, they can pick any point in the middle here. Okay? Guarantee temperature changing, they cannot be cut off, they cannot be saturation. Okay, another one. Okay, let's see. This set curve, also family curve, we already done. Okay, let's see here. Now, that given you a little more explanation. This like cut off, they like open, switch. Okay, that means you get IVB 0 volt, IB equals 0. So the transistor will be open. Collector here, and that collector and the admitter open. So no current flow. That like switch open. Okay. And now you can see saturation. Okay. When you apply the voltage at the base, and they will be transistor will be on, and they on, and they will be saturated. Saturated, that means the voltage from C to E here almost 0 volt. So that's why it look like they connect to the ground. That's only telling you if they open, the voltage here will be 5 volt. if we get 5 here. Okay, in the binary, 5 volt will be a logic 1. And when they working, they close. So the voltage at here now will be 0 volt. And that's why they will be logic 0 to build the logic circuit. Okay?
What was
On the
VCC?
textual, then this Wednesday you're learning about the logic gate. You can understand more. Yeah,
What was VCC on the saturation one?
no, same thing. 12 volt, 10 volt, any voltage. Only thing is you try to draw more current. That will be dry it to saturated. That means no more gain, no more amplify. Only thing now, I want you to understand what it means cut off or what that means for saturation. They working like a switch, okay? However, they can using transistor saturated to build the logic circuitry, okay? Now, we go into the circuit here. Before we can do anything, then the transistor needs the power. That means the DC power. That's what we call DC bias. We need the power supply DC to make the transistor working before we can do anything. Okay? The thing is when you're doing build the amplify, basically transistor will be doing nothing with the power supply. They only deal with the void. Your void, you get input sideways. Output, they can get a bigger sideways. However, without the power supply, then the transistor not working. So that's what we're talking about, DC bias. Okay? And now you can see on that one, you can get IC coming in, IA, and that will be IB. And the voltage here, 0.7 volt. Okay? Now, in order to do calculation, so if you know the IB, you're able to know IC, you're able to know IE. Okay? So normally they can using in this configuration, they need two power supply, one VBB and another VCC. Basically, they don't want it. Okay? Later on, you can see. But these are very basically thing we need to know. If you want to draw the loop for the current here, normally you draw the loop flow this way. Okay? So when they hit into VBB, they hit into the negative here. Then you say minus VBB. Okay? When they go to the resistor RB, and this side positive, this side negative, and the voltage across RB you must be adding plus VRB. Then when they go into this diode here, you get 0.7 volt plus here minus here. So you have to be plus 0.7 and everything equals 0. And now from this one here, then you can see what VRB equals. VRB.
VDB minus 0.7.
Now IB times RB. Right? That is the voltage across RB. Okay, let's see. I want to make sure if we get a guest already into the meeting, please let me know so I can stop. Okay, so make sure VRB means the voltage drop across RB. So now you can get, I want to keep that side here and have to move that to the right, the other to the right. So VRB equal VBB minus 0.7. And that will be IB times RB equal VBB 0.7. So that given you IB equal VBB minus 0.7 divide to RB. Okay, but you don't worry about that thing. They will be given to you if you want. They want calculate the IB. Okay, and now you can see right here. See that VBB minus VBA divide to RB. That's what you get IB. By the way, I given to you a few things more. Okay, first thing you understand is IC beta times IB. Okay, that formula using all the time. The next one, we don't want to use IE equal IB plus IC. This formula we don't want to use. Okay, if you want to calculate the IB, then better using that one. IE divide 1 plus beta. This is the formula we'll be using.
Mr. Pham,
Yeah,
the counselor's here.
okay, they already here?
Yes, Sandy Hamel is here.
Okay, I will be stop there. You guys please wait for a while, okay?
Hi, Carl. How are you doing?
Pretty good. How are you? Thank you so
Pretty-
much for
pretty
having
well.
us.
Okay. Yes. So you on? Go ahead and share. Okay, Mr. Pham. I think we're good to stop sharing the screen.
Yeah,
Okay.
Sandy, you want to go first?
Yeah.
Go
quick
ahead.
intro.
Okay.
Hi, Mr. Pham. Thank you for having Carl and myself come into the class today. We are both part of a team of career services professionals that's here to cater to students who are looking for work, whether you're transitioning into a new field, looking for a necessity job while you go to school, and we also stick with you up to a year after you complete your programs. So I'm a job developer, and I work with students in the skilled trades fields. And so electronics is underneath my umbrella of students, and I'm definitely here to make myself available for you guys. I have a pretty open schedule. I can connect with you via phone call or Zoom. And I just wanted to make sure that you guys were able to put a face to a name if you ever see emails come out. Another big thing that I'm trying to really start to do with electronics is get some professionals in front of you guys. And I want to do that through inviting employers to come in and speak with you guys so they can speak on an industry level of what they're looking for when they're hiring, what skills they want you to come in with. They can get a good feel of, you know, what Mr. Pham and your instructors are giving you, and they can see how that transfers into the real life setting for them. So I'll be working with your instructors to coordinate some of that, but I definitely wanted to just let you guys know that even as we're remote, you have a community of professionals that are here to support you through student services. Carl's an amazing counselor, and I know he's going to go more in depth with what he can offer you, but just so you know, you can contact our department. I'll send out an email with our contact information detailed, and we'll be here to support you. But other than that, Carl, the floor is yours.
Awesome. I'm going to see if I can share my screen. Thank you so much, Sandy. You basically encapsulated everything that I was going to talk about. I'm just going to reiterate a few things here and there. Basically, as a career counselor, I'm here to help you. And I'm the only career counselor for the San Diego Community College, for the San Diego Continuing Ed at this point. So covering 7 campuses. How many of you have met with a counselor before? Probably during orientation or maybe in a categorical program. Maybe you raise your hand, show your hands. Because understand that there are counselors, right? But typically they're assigned to a specific program. I'm different because basically my specialization and my line of expertise is in helping you develop your career. You should be seeing the screen now to explain what career counseling is. It's a process to help you understand yourself and the world of work in order to make career and educational decisions. So I'll skip through the bottom of this infographic here to the bottom. It says, need help with any of the following? So if you're interested in help when it comes to career or major exploration, if you're interested in learning about the labor market, information regarding the field that you're considering or fields that you're considering, if you're interested in maybe taking a career assessment to maybe analyze the options that you have of the ones that you've considered and the ones you haven't considered, maybe you're transitioning from one career into another, or one job to another, or other related career related services, I can help you with that. So it's a process to help you understand yourself and the world of work in order to make career and educational decisions. That's what career counseling is. And so I understand that we all are very busy with what we're doing at school and what we're doing professionally, and combining that together will really ready you for what's next for you. So a nice little quote that I always share with people is, choose a job you love and you'll never have to work a day in your life. Who wouldn't want to do that, right? So basically you're working, but you're not really working. How's that sound like? All in all, and I'm not sure who actually wrote that quote, because they were so happy after they found their job that they forgot to get credit for it. Another thing that I want to go over really briefly is kind of a visual representation, a mental model of the career development process. Typically, I start in the upper right quadrant, which is the getting to know yourself phase. And this is when we can learn about your interests, your skills. You can share some of the values that you have, and maybe we can get some insight on your personality and fit with that personality. Then after we spend some time getting to know you, then we'll explore options. So that could mean, completing a course at Continuing Ed, or maybe a certificate, or maybe moving on into an associate's degree program, or even a bachelor's or master's, or even a doctorate, right? And some people can go all the way to, the upper echelon of options academically. And then obviously to pair with that are professional tracks as well that will lead you into better and better positions potentially. After we explore options, we take a look at getting focused, which means, some people may need some help when it comes to the decision-making process or priority or setting really the stage for what's next, which is the take action step, which is what Sandy specializes in, right? And I can help you along with that as well. That means connecting you with employers. That means getting you more familiar with the job repositories that exist. That means maybe preparing you for workforce entry. So there's a lot that goes into that. So to get a hold of me, it's very simple. Again, my schedule is very flexible. You can email me and then we can correspond. And again, I can be your sounding board to the ideas that you have with where you want to take your career or where you want to start your, maybe your job entry possibly. You can also call me or text me at 619-808-1000. So what I'll do is maybe I'll copy and paste this to see if it works. First time I've done that. And I'll put it on the chat. See if it works. Yeah, it works. So there you go. So you can get a hold of me. You have it on the chat. So please connect with me anytime you need me. Again, thank you so much for giving me the floor. And I know you guys are going through very difficult subjects right now and topics, because I was lost as soon as I logged in with all the electronics diagrams that you guys had. But the hope is maybe you can share a diagram for you in regards to your career, right? So thank you again, and I hope I hear from you soon. Also, I want to share a workshop that I'm going to be doing in a couple weeks, which is about career assessments. I'll actually just forward it via email, and then if the professors can share it, that would be amazing. So Professor Pham can share it after I send the email. So thank you so much.
Thank you, Carl.
Yeah,
Thank
no
you,
problem.
Sandy.
Thank you.
Well, let me stop sharing because I know it's not my class.
Okay.
So see who can get any question.
I have a comment.
Go ahead.
Hi, my name's Lowell Ellis. I understand that what you're trying to do is notify the students as to your services. The only issue that I see with trying to notify students is they're only being notified when they decide to be a student. When you sign up to be the student, we don't necessarily have on a daily basis persons like yourselves wanting to try and notify people and put into their minds all these possibilities and decisions that they can help to build their futures, mainly where to look, all the information sources, how they can be stimulated to reach out and start looking for people such as yourself who have that structure that you're wanting the students to be fortified with. So basically what I'm getting at is when I go to the portal to sign into school, I see basically one page that's just for sign in. Or I'll go to, like, say, this class website, and it'll be specifically the introduction or the showing of the class. Or say if I go to like the news would be just a little off topic, but how society can be stimulated as to where they can be notified as to your resources so that they want to be stimulated to become students again,
right?
And locate the steps or know the resources and how they can be stimulating themselves again to just be educated or be involved in society somehow. So basically it gets down to, at what point do we need to look around on a website for your resources versus going to the front page and your resources are like the first thing that pops out.
Right.
Counseling can help you be educated today, or I'm sure you can come up with something. You understand what I'm
right.
getting.
No, I think I get what you're saying, and I share the same sentiments with you. I wish, because there was actually there was a presentation from researchers for continuing ed that indicated that there was a need for students to learn more about the career development process on the front end, even before they become a student, and throughout as well, right? Because that's when you're in your most and when you're looking at options before committing to programs. So I get what you're saying. And there are some challenges to that because basically the roles that we have are tied into funding, number one, which means we're mandated to, for the most part of what we do, to serve the students that are already enrolled in the programs that at continuing ed. Okay. I wish we could serve more. And if someone reaches out to me, I usually do, and they're not students, I will still serve them in some capacity, and I'll also share with them some resources that they can get career counseling outside of San Diego Continuing Ed. One of the things that we're doing to alleviate that, and this is just in the early stages, is we're actually, I'm actually developing a workshop called Your Best Career Fit. And essentially this is for any student continuing ed, as well as non-students who are just inquiring about the programs that we have, okay? Just so that they can get a first snippet into not only the programs that we have, but just a little bit of the career development process. It won't be super in depth, but it's at least an introduction. The workshop I'm doing in 2 weeks. And so if you have friends and colleagues who are non-students who may be interested in continuing ed, please refer them to the link that you'll be seeing here shortly in a day or so when I forward the information to your professor. And then that's kind of the start of kind of, addressing that particular issue. I wish there was a way that, we could just share the insight of not only, career development, career counseling, career and job resources before they become a student. We do have some parameters typically that we work with. I hope that answers the question, but I'm with you. I wish it was pervasive and it was on the very front of our website. With that, let me actually, and I apologize for taking a little too long, but let me share with you how to find our website, or specifically the section that we have from the website. So if you go here, you go to Student Services, move some things real quick. Yeah, then you'll be able to click on Career and College Transitions. So once there, you can learn about the services that we provide. You can have the contact information of not only the job developers, but of course, the services that I provide as career counselor. And that's how to get a hold of us. And that's how to connect with us. I hope that helps. I know it's not like the definitive answer, but I hope that at least provide you with some guidance without taking up the entire class, because
Thank
I
you.
don't want to do that.
Does the Metro Career Centers kind of handle that before?
Yeah. The Metro Career Centers are free services. You're right. The Metro Career Center services, they're free and they're for the general public.
I don't know if you're actually able to answer this question or not. Do you ever foresee the lab portion of this class ever opening up again, or is it going to be this way for a while?
Of course. I can't tell you when. I can guarantee you eventually it will, right? But in terms of timeline, it's beyond my scope of decision making, of course. Typically there's program counselors tied to specific programs, and they don't even call the shots. It's the department that calls it, and then they don't necessarily call the shots either, because there's an institutional mandate. And then if you go above that, the state of California has mandates. So there's a lot that goes into it, right? And they're all carefully thought of. But I can tell you, I know it's challenging now. On the flip side of things, the cool thing is you guys are learning some really good tools that you wouldn't have otherwise been exposed to, right? Because of the shift in use of technology now. Now you can say, hey, you're a Zoom expert. You know how to do online learning. Of course, a lot of people will say and argue, and they're probably correct, it's not the best modality for most subjects, right? Especially with something that involves more tactile and hands-on approach, like electronics, right? But all in all, it's a modality that now you're gaining more familiarity with. And
So we'll be
forward,
doing this for about a year.
I don't know the timelines, and please don't quote me anything. But I hope it's
Okay.
coming soon.
Thanks,
Hey,
Bob.
Joseph, I'm with you.
Okay.
Just
Thank you.
just one last comment. You were saying something about funding and having all the various groups involved with having anything a classroom be started or end. Is there a student survey where you are asking students to fill out their future intentions to where you can stimulate funding, like say as some type of Google Doc?
I mean, they have researchers that go out, and that's their job, is to connect with students and get a sense of where they're at, where they want to go, and the temperature when it comes to that.
But as far as
But
having students or future students make sure that any state funding is available, are you generating a form that's some form of stimulus to make
I'm not
sure?
generating any stimulus forms or, anything regarding to funding or anything like that, because
Right,
that's not
exactly.
really
And
my
that's what I'm
role.
getting into, is at what point do those forms have to be generated to make sure that the students have this type of education?
I would say, I mean, if you have concerns like that, I mean, I would escalate it up to, I wouldn't hesitate to escalate it up to administrators to let them know your sentiments as a student, the challenges that you have and the interests and wants that you want as a student, right? Like for example, like vice president of the student services or the president of the institution, they're pretty, open when it comes to taking in, communication from students. And those are really important concerns, right? And it's from a well thought of place, and so that's where I would do if I were you. And then you can connect with the campuses that you're involved in as well, and they might be able to point you in the right direction.
So as far as counseling, you're not necessarily tapped into where you can take those suggestions to your board meetings and try and get that thought stimulated?
Not necessarily. I mean, I share it with my administrators. I mean, I refer to labor market information that is objective usually when I make recommendations. And
Yeah,
so,
that sounds good. Yeah, just recommendations, get the thought
yeah, of
in the
course.
circle, and then have people start working with it.
Yeah,
All right,
yeah.
that's all I have to say. Enjoy your evening. Thank you for what you do.
Thank you. Okay. Well, I think we'll be leaving now. Thank you so much for your time, guys. Appreciate
Thank
it.
Hey,
you.
thank you,
Thank
Carl.
you.
Thank you,
Bye-bye.
Sandy.
Thank you.
Okay.
Thank you. You guys.
Okay, back to class.
Thank you, Sam.
You're welcome.
Okay, so now coming back, you guys do it for me.
Mm, 28, 2020.
Okay, that one we already done. Okay, now you do it for me. For this circuitry here, they want to calculate IB, IC, IE, VE, VB, VC, VCE. If you get the answer, let me know.
43 milliamps for IB.
Okay, we'll see. 0.043 milliamp.
Oh, don't change it. I didn't realize that. Thank you.
When I say IB milliamp, I want milliamp answer. If you want calculate IC equal beta times IB, beta they given you 100. Okay, who get IE? The formula calculates the IE equal 1 plus beta times IB. That's the formula we want to do. IE equal 1 plus beta times IB. They come up with 4.34. So you can see ICIB very close. And now VE. Easy, right?
Everything's easy.
VE means from emitter to the route. That means from here to the route. Huh. I didn't see they give it to you. VE. VE equals 0. Who got the VB? Can you guys do it?
0.7.
VB. That means the voltage from the base to the route. Equal what? You can see it right here. They already gave it to you right here. From the base
4.3 volt.
for 0.7 volt. You can see it right here. Base to the route. That means
VBE.
0.7 volt.
VBE equal VB, right?
Right. The thing that is routed here. No resistor for the emitter. So VE again, from emitter to the route, they will be 0 volt. VBE, that means VB. In this case, equal 0.7 volt. VC, VC means from the collector to the route. Okay? So the formula equals VCC minus
VRC.
IC times RC. You take 12 minus 4.3 times 1K.
7.7.
So I can tell you answer. 12 minus 4.3. 7.7 volt for VC.
Hey, Mr. Pham, we said the VB is the same as VBE, right?
VB, right?
Right.
VB means from the base to the route, and E connect to the route. So that's why VB, same thing with VBE.
Right.
So if you're doing a right one, VC equals 7.7.
Mr. Pham, could you repeat, please, the value of BC?
V, what V? VB?
No, VC.
Oh, VC. VC means the difference between VCC and the voltage drop here. The formula will be VCC minus IC times RC.
Thank you.
Welcome. So answer will be 7.7 volt. And the last one, they want VCE from C to E. VCE equals VC minus VE. And you know VE 0. So VCE also equals VC. 7.7 volt. Try to understand it so you can do your homework easy. Okay? So we move to the next. That's what they given you. VE 0, VB 0.7, VC 7.7, VCE 7.7. The thing is, sometimes you can understand, you never have to do your calculation. The thing is, you get the simulation. You want any voltage, any current for the circuitry. You run simulate, you can get everything. However, we just bring it up to make sure in case, interview, they can asking you. They not want you to do calculation, but they asking you, how do we calculate the VB? When they say VB, only B. The other side must be common, must be round. That means from the base to the round. VC, that means from the C to the round. Okay, now you can do this thing for me. Only the difference now they given you RE right here. They want to calculate the IE. That means the current flow here. And you understand voltage from here. How many volts?
0.7.
Exactly, 0.7. So if you want to write the loop, you can say they go here. They hit to negative, so will be -5. Okay, then they go here. They hit to the plus 0.7, so they plus 0.7. Then now they have to adding to the voltage drop here. That means IE times RE.
So, Mr. Pham, so you're saying that would be minus VBB plus VBE.
Plus 0.7.
Okay, wait a minute, hold it. Minus VBB plus 0.7 plus IERE.
IE times RE.
Yeah, right.
That's why you can calculate the IE.
And then once you get all that, then you'd say equals 0. That's how you write the equation.
Yeah, if you don't want equation, you can say you want to calculate VE here. Okay?
Hey, can you write that down with your little pad thing?
Okay. That means, how can I do? I can stop that one. Okay. Say answer. Okay, so now I can given you okay, if you want to doing the loop, then you start with minus VBB. Okay, then you plot 0.7. Then you plot IE times RE, and that equals 0. I want to make it bigger. Okay.
You're using the picture?
Then now you can say you get IE times RE equal. You take this, go to the other side, so you can get VBB. Okay, minus 0.7. And from here, easy to calculate IE equal. Okay, VBB is 5 minus 0.7, 4.3. Okay, divide to RE, divide to 2.2K. Okay, another way, you can calculate the VE. Now, if you're looking here, VE right here. So you get 5 here minus 0.7, you get VE. So you can get VBB minus 0.7. And that's why you can get 4.3. And now you can calculate easy IE. IE equal VE divide RE. This the second way, much easier. So that's why in the answer right here, VE equal 4.3. IE equal VE divide RE, 1.95 milliamp. Now, if you want to calculate the VCE, you need to know VC. You already know VE. VC, okay, I give it to you. VC equal VCC minus IC times RC. Okay, then VCE equal VC minus VE. So VC you calculate, you get 15 minus 1.95. So you're able to get the answer. VC finally 13.05 volt. And if you want VCE, you take 15.05 minus VE is 4.3 volt. If you've done it, let me know. We can go to the next.
DC is 13.05 volts, so VCE is 8.75 volts.
VCE, okay, equal VC. VC, you get 13.05 minus 4.3. Let's see, 13.05 minus 4.3. 6.75. for VCE. 6.75. Okay, that equals 6.75 volt.
No, it's not correct. Around 9.02.
Would it not be 8.75? You got the 13.05 volt minus the 4.3 volt. That should comes out to 8.75.
Is it 6.75? It's the right one?
Well, you got the, I look at your calculation here. You said VC was 13.05 volt, correct?
Right, minus 4.3.
And 4.3, that comes into 8.75 volt.
Okay, I got calculator wrong here.
Okay.
Okay, I tried. No, let's see.
Because if you use 6 plus 4, that's come only about 10.
13.05
Yeah, so it,
minus 4.3. Oh, I think I read the wrong one.
yes, sir.
8.75, right?
Yes, sir.
Sorry.
You're forgiven.
If you're still confusing something, bring it up. Okay, anyway, you understand this is the first time we run electronic and a digital online. Okay, so on off the tech 1 and tech 2 must be complete assignment for the tech 1. Also, tech 2 have to complete assignment for tech 2. Go into the next semester mean spring. Who already in tech 1 now, you complete assignment for tech 1. You go to the tech 2 on the spring. You don't have to do anything with the tech 1. Only thing what I try to do, I try to give you the basic understanding. You know, you can do the job. The thing at this time we can 180 degrees the way we teach it, okay, for online. Okay, so now we're going back. Another way for DC bias, that's what they call a emitter feedback bias. They say better than the Bay bias, that's what we just do it. Kill points still move and not popular. I just bring it up for you. When you see the circuitry, you know that's what they call feedback, emitter feedback. But we not do any calculation, anything. Next one, Bay bias. That will be the least predictable. Kill point move with replacement keeping move with temperature, not practical. So that's why you never see this circuitry being designed in the circuitry at work. This is the one they call a collector feedback bias. Better than emitter feedback bias. Q point still move. Limited application. I already talked to you a Q point. That means they select a point in the active or saturation or cut off. So they don't want it to be moved. But that one they moving, so they not really good. To supply emitter bias. Now, if you're looking on that one, you see power supply here, and also a negative power supply here. Okay, that's very stable. However, require two power supply. They don't want it. They want using only one power supply. Okay, the thing it cost more if you need two power supply. Okay, so for now, I can skip this one. Okay, you can look into that already given you. How to calculate the VC, how to calculate VCE. We're coming back when we get the time. I try to get up to the point we want. This is the one we want. They're using the voltage divider for bias. That means they're adding two resistor R1, R2 here to get the voltage at the base. Okay? So save a lot of money. The thing is, two resistor cost you maybe 50 cents. Why you need a another power supply cost more? Okay? So this is the circuitry normally being used. First thing, if I want to calculate the voltage at the base, VBB, so you get a VCC here, R1, R2 voltage divider. This is the formula. VBB equal VCC times R2 divide R1 plus R2. So that's easy to calculate the voltage here. After voltage here, you already have it. You can calculate the voltage at meter here. How? The difference between VBB and VE is 0.7. So you want to calculate the VE. You take VBB minus 0.7. So after you get the VE, you want to calculate the current IE. Take VE divide IE. That's what they show here. Okay? And now if you want IB, using this formula, okay, IE divide beta plus 1. Okay? And if you want to calculate IC, you're using beta times IB. If you want to calculate the voltage drop here, then you take IC times RC. Okay? Finally, you want VC, that means right here. Then you take VCC minus voltage drop here, ICRC. Then you get VC. If you want VCE, then you take VC minus VE. This circuitry using all the time. Now, I get about few more minutes. Try the best you see who can get VBB, VE, and IE. And make sure you understand tomorrow we will be teaching you on the C++ programming. We will be need that. If you get the answer, let me know. First thing VBB.
I had a question about the previous slide. It says IE equals VE divided by IE.
Right.
But we're trying to figure out what IE is.
VE, you need to calculate the IE, right?
Yes.
You take VBB minus 0.7 here, you get VE. After you get VE, IE equals VE divide IE.
Hey, Mr. Pham.
Yeah.
On these transistors, it's a given that all the time VBE is always 0.7, right?
Right, for silicon.
Okay.
For now, forget the menu.
Okay, so anytime you give us a transistor or something, it's always 0.7 unless you tell us otherwise.
Right. They not deal with the menu. The difference is 0.3 and 0.7. Quickly, who get VBB?
Is it 3.58 volts?
3.58.
EE will be 2.88 volts.
Very good. Quickly, if you get it done, we do perfect job today.
That starts with the letter E.
I said you must be doing your assignment, okay? Otherwise, the student asking me they get enough for 150 hours. How come we cannot get through? You must be meet school requirement. You have to do the job in the program. Otherwise, I let you stay. No big deal. You can stay forever.
IE is 5 milliamps.
5.1 milliampere.
Hi, IB. If you understand, everything will be easy. We do not do much of calculation, okay? But at least the minimum thing, you have to get through it.
.05 milliamperes.
Very good. For calculation. So quickly, whoever gets.
5.1 milliamps.
Perfect.
.1 volts for VRC. VC is 4.9 volts.
I get 4.89. Who can get the same?
Yeah, 4.89.
Okay, good.
VCE is 2 volts.
Perfect. Okay. Whoever not done, copy it. Okay, any question? Is it I'm running too fast or too slow?
Okay. Are we going to get into multiple transistors later?
I couldn't hear you.
Are we going to get into multiple transistors later?
Yeah, everything.
Okay.
The thing is what we want to do for your guy is what? We'll be trying to deal with the problem. That means at the company to testing, and now if you get something wrong, how can you fix? That's what the main thing we want. But the first thing I have to give you the basic understanding. Then we have to deal most of the time, try to deal with the circuit. Something wrong. What can we do? Okay, so if we don't have any more questions, we stop here and we'll see you guys tomorrow.
Thank you, Mr. Pham.
Thank you.
Thank you.
Thank you. Thank you.
Thank you, Mr. Fan.
And thank you, Sam, for the questions.
Thank you, sir.
Okay.
Thank you, Mr. Pham.
You understand that make me happy. Okay?
Thank you.
Thank you, Kumi.